Welcome back. This is the first lecture on dynamic regression models. I need to warn you, this is a very large topic, and you could potentially spend a much longer course studying this topic alone. I think the author of your textbook has done a very good job of taking this large area and putting it into a manageable chapter that we can cover in a week. So I plan to cover all of Chapter 9 except for the section on harmonic regression models. Then I'm going to cover one of the sections from Chapter 11 that gets used a lot in marketing. Remember the first week I said forecasting is really used for three things. So the first thing is for description, second thing is for prediction, and the third thing is for prescription, where prescription means that we're trying to understand how other factors that are under our control relate to the dependent variable that we're studying. This is going to require using regression models, and so we'll be building on what we did in weeks 2 and 4 and kind of combining those two things together. So let's have a quick review of traditional regression analysis. So remember, with regression, we assume that y is some linear combination of predictors. Now, back in the regression class, we had p predictors. Since p is used for the autoregressive order, I'm going to use k as the number of variables that I have. Then, importantly, we assume there are errors that are independent of one another and homoscedastic. So that is the traditional regression model. What we're going to do this chapter is to assume a very similar model. So it's exactly the same linear combination of x possible predictors, but instead of having epsilon, we're going to have an eta as our error term. This is really important. Whenever you see an epsilon in this class, you should think white noise or Gaussian white noise. Whenever you see an eta in this class, you should be thinking that the errors have some other distribution. So we're going to write it like this. Eta may have an ARIMA distribution with 1, 1, 1. So this would be one difference, one autoregressive coefficient, and one moving average, which we've been writing in backshift notation as follows. Then what we say is these etas are white noise. So it's very important that we be able to write equations like this. What would happen if we had serial correlations between our errors and we just fitted a normal regression, a basic regression? Several things go wrong. The first thing that goes wrong is that the estimated coefficients will still be unbiased, but they're not going to be blue. So if you remember from Stat 1, what blue means is they are efficient, that they are the best linear unbiased estimators. The OLS method of estimation does not give the most reliable estimates. We could do better if we took advantage of what we know about these different errors, these etas. More importantly, what's going to happen is that our standard errors and t-tests will all be wrong. So we're not going to be able to trust any of our inference methods. We can't trust the confidence intervals, we can't trust hypothesis tests, we can't trust AIC. I believe these are the biggest problems that we have, although it would be nice to have efficient estimators also. So what we're going to find is if we can model the etas with an appropriate ARIMA process and then estimate it using maximum likelihood or by minimizing the sum of squared epsilons, not the etas, the epsilons, then we can avoid those problems and our inference will be correct. Let's talk a little bit about model building now. Here is our basic ARIMA model. A few rules that we have to follow. So number one is all of the y's and all of the x's have to be stationary. So if they're not stationary, our estimated coefficients can be incorrect or the standard errors will be incorrect. And so we want to get them to be stationary. So how do we do that? Well, we're going to take differences whenever we have non-stationarity. Now, when we do our differencing, we usually take the same differences to all of the variables in the model just to preserve interpretability. Recall that any ARIMA process can be written as an ARIMA process through differencing first. Let's see how that works. I'm going to assume just a single x, so I don't want to have more than one subscript in this class if I can avoid it, and therefore let's just have one x. And what my claim is, if I difference the x's and the y's, I'm going to end up with an ARIMA process. So let's go write that out. I'm going to go over to my document camera. So this was my model. Y sub t is equal to alpha plus beta 1 times x sub t plus my errors eta t. So if this were non-stationary, I would compute differences. So what is y prime at t? Well, that is simply y, that's a y, t minus y, t minus 1. I'm going to go drop in the definitions of both yt and yt minus 1. So yt is easy. That's just this thing up here. So alpha plus beta 1 xt plus my eta sub t. What is yt minus 1? Well, that's going to be minus alpha minus beta 1 x t minus 1. And then we're going to subtract off an eta t minus 1. So think of this as y t minus 1. This whole thing right here is yt. We can see the alphas cross out. We don't really need an intercept when we've done the differencing. And I can collect some terms. So this is just going to be beta 1 times x sub t minus x t minus 1. So I'm just combining this and this term to produce what I have here. And then I have eta t, but what do we see here? This is just the difference of xt's. This is the difference of eta t. So the point I'm trying to make with this is that when I take differences of my y's, that also implies that I'm taking differences of the x's and of the etas. When we look at our errors, here are the original ARIMA errors, but this term says take the difference of the etas, and what I'm left with is an ARIMA process, an ARIMA 1-1 process in eta prime. This gives me my AR1, this gives me the MA1, and all of this is in eta prime. So by differencing, we've produced an ARIMA process. So when we fit our models, this is the procedure we're going to use. We're going to rely very heavily on AutoArima to help us find the right number of differences, the right number of moving average terms, and the right number of autoregressive terms. We're then going to check our epsilons and make sure that they are white noise. So we're going to be using the KPSS test in order to confirm that. If we find that these epsilons are not white noise, that means that we need to do more with our ARIMA model. And so we may make some custom changes to what came out of AutoArima until we can reduce everything to white noise. Once we have white noise, then we can do model selection using AIC. So we'll be repeating this procedure for different sets of predictors. So sometimes we may have, say, 3 x's, and we might find that one of those x's actually makes the corrected AIC worse, and we would drop it then. I'll just mention a lot of other textbooks and software packages use hypothesis tests instead of AIC to do this model selection. Our textbook author recommends using AIC, but you'll often get exactly the same answer when you use t-tests. Let's go look at an example now. This is the US change data set that comes with the libraries in our book. So let's go over to R and take a look at it. If we look at the help page, what we see is that we have economic time series from 1960 to 2016. So these are some commonly studied variables in economics, things like personal income, consumption expenditures, production savings, and the unemployment rate. Now, one thing that's very important to notice about this is that they are percent changes. So percent changes are where you take the current value minus the previous value. So that's really just a difference. Divide that by the previous value. Because of this differencing, I expect this to be pretty stationary. So I'm going to go generate time plots for this. Now, whenever you have multiple time series, as we do here, an option that's very useful is this facets equals true. That generates a small multiple, so a small version of each time plot for each one of the 5 variables in this data set. These time plots show strong stationary patterns, so there are no trends. So I think because of the differencing, this is a very well-behaved data set. If you don't believe me, we can go use our KPSS test. The test statistic is very small. It's much less than even the critical value for a 10% cut. If we do it for the second variable, same story, third, fourth, fifth. All 5 variables have very small test statistics, less than the critical value for the 10% cutoff, so they're all very stationary. So if we follow our procedure, we're going to use AutoArima to choose the right model. Then we're going to check our errors. So let's go do that. The textbook tries to understand how consumption depends on income. I'm going to see how consumption depends on savings as a slightly different example for this video. We're going to use the AutoArima command. The only thing that's different from what we've been doing in Chapter 8 is we're going to add an xreg argument that specifies a list of the x variables. Let's go run this. Before we try to interpret this, let's go look at our residuals, because if the residuals are not looking good, we're going to have to make some changes. So let's not waste our time interpreting this until we know that we have a good model. When I look at the residuals, I don't see any patterns. I've got a borderline significant third autocorrelation coefficient and maybe something out in the 20s. When I look at the Young box test, though, the p-value is pretty large, indicating I cannot reject the null hypothesis that my residuals are white noise. Therefore, I think this is a decent model. We can then interpret this. AutoArima has selected the following model. Let's talk about what each of these things mean. So this 4 is indicating that it's selected a seasonal ARIMA model and that there's 4 periods each year. In this case, we've got quarterly data. So the first triple is giving us the usual ARIMA values. So we have 1 autoregressive term, no differencing, and 1 moving average term. The second triple is giving us the ARIMA values for the seasonal part. This is saying we want 2 seasonal autoregressive terms, no differencing, and no moving averages. Here is the estimated set of coefficients, and it's very important for you to be able to get from these estimates to a set of equations like I have below. So let's start with the first one. The first one's the regression equation, and so y sub t is just equal to the intercept. So here's our intercept, minus 0.0085 times the x variable. So in this case, my x is savings, my y is consumption. That negative coefficient tells me that as my savings goes up, my consumption goes down. And that makes a little bit of sense in that I guess if I'm saving more of my money, I'm not going to be consuming as much. The last part of this equation is one of these eta errors. So eta is not white noise. Eta is going to be some sort of ARIMA process. So the next equation tells us exactly how we get these etas. Now let's talk about forecasting. So if we want to forecast from one of these ARIMA models with x variables, we need to know the x values into the future. So sometimes we'll know these x values. For example, maybe one of our x's is advertising. If we've budgeted our advertising spend into the future, we would know we're going to spend this amount next month, this amount the month after, and so forth, and we would be able to insert those x values into the model. Otherwise, you may need a separate ARIMA model to forecast the x's into the future and then drop those into your forecasting model. I've used the model that I built on the previous page to do a little bit of forecasting. So we'll use the forecast command as before, except that now we're going to add an xreg argument. So to keep things simple, I'm just going to take the average of the savings values as my future savings. We'll project this out 8 periods. We can create a forecasting plot with confidence bands. I should note the prediction intervals here don't account for the uncertainty in the predictors. I'd like to do one more example with us today. I call this the Blaisdell example. I've taken it from a book that I used to teach from. This is the Kuttner book. So Blaisdell is some company that wants to understand how its sales depends on industry sales. So they'd like to be able to see if they can predict how good their sales are based on how well the rest of the industry is doing. So the first thing I'm going to look at is a scatter plot matrix, and what we see is that Blaisdell's sales track the industry sales very well. It looks like when the whole industry is doing well, Blaisdell does well. When industry is not doing so well, maybe there's a recession, or maybe demand is just down for whatever this product is, then Blaisdell's sales also go down. So it's an extremely strong relationship. I would guess the R squared is up around 0.99. Let's go back to the course packet, and I'm going to fit a linear regression. The reason I'm going to do this is to show you that there are problems when we use linear regression. Here is my linear regression output, and I'm going to go state an estimated regression equation just as we did on the previous slide. So my intercept is minus 0.455. Now the slope is estimated to be about 0.176 with a standard error of 0.0014. What I told you on the first slide was using OLS will give us unbiased estimates of the slope, so that's going to be fine, but these standard errors are going to be wrong. Likewise, the sigma squared will also be wrong. So these two numbers are wrong, and remember, this is what we use to compute confidence intervals, it's what we use to compute hypothesis tests, so all of those things are in question when you use OLS. You might be wondering, where did I get this number? It comes from an ANOVA table, so 0.007. It would also come in the summary output, but it would come as a standard deviation rather than a variance, so we could square that. That could introduce some rounding though, so I'd rather just pull it from the ANOVA table to get it a little more exact. The next thing I want to do is look at my residuals from this model. And what we're going to see is we're going to reject the null hypothesis that we have no autocorrelations. So that's going to be a signal that this OLS regression is not valid. We need to do something else. What should we do? In the course packet I said we're going to use AutoArima to help us figure out how many autoregressive and moving average terms we need. The next thing that I'm going to do is use AutoArima. However, there's a problem with what we're doing. So the problem is we don't have stationary data. So remember, one of the requirements is that both x and y need to be stationary. And so if they're not stationary, we need to go take some differences. When I look at my scatter plot, this is not a stationary process. My y's are seem to be going up with the x's. They go up with time. Perhaps what's happening is the economy is just getting better. We're growing with GDP, something like that. So putting this into AutoArima is not going to be correct. But let's just go see what happens if we do something that's incorrect. What comes back is AutoArima says we just need an AR1 model. And if we go look at our residuals, the residuals are signaling we have some problems. So I can reject the null hypothesis that I've got white noise. This is saying I've got some work to do. So something's not working right. So let's go state the estimated regression equation, even though we don't have stationary data and the model's not correct. Give us a little bit of practice. Here's our intercept, minus 1.28. The slope is sitting right here. And notice now how different the standard error is. The standard error is almost twice as large as what we had with OLS. Let's go take a look at our errors. So remember, we have an autoregressive process. And so our current error is going to be 0.6295 coming from right here times the previous error plus some new random noise. And that new random noise is going to have an estimated variance of 0.0047, which I'm going to just write here. Notice we have quite different errors, so 0.0074 versus 0.0047. So it looks like variance of our epsilons is much smaller than what we had with OLS, and our standard errors are much larger. Let's go do this the right way. The right way would be to take some differences. I will first compute differences of both of my variables. Here's the difference of the y data, difference of the x data. I'm not going to include any autoregressive or moving average terms because I think the differencing is going to take care of it. So before I go interpret this, let's go look at the residuals. We see now our p-value is massive. We can't reject the null hypothesis that we've got white noise errors. So that's a good thing. Let's now go try to interpret this estimated equation. So this is saying my differences equal 0.1685 times the difference in the x's. And then I have a slope plus some set of errors. Since I don't have any autoregressive process, these errors are just white noise. Now notice how close this slope is to the slopes that I got with OLS and with the other incorrect model. These were unbiased officially. However, the standard errors are quite a bit different. So the standard error is 0.005. That's twice as big as what we got with the model with the non-stationary data, nearly 4 times as big as what we got with OLS. So the standard errors are incorrect with these two models. You'll notice the second model with the stationary data, though, gets pretty close on the errors. So 0.0048, 0.0047, that's pretty close. Let's do one more model. So this is a much simpler model than the ARIMA 000, although it's equivalent. And so the idea here is we're just going to use the LM function to regress the differences in y's on the differences in x's. We don't even need an intercept. So that -1 says get rid of the intercept. And notice we get exactly the same parameter estimate, the same slope estimate, and our standard error is about the same. I'm not quite sure, this may be rounded incorrectly. I would expect them to be exactly equal. Either of those models are correct, and they give the exact same estimates. I want to talk about one more topic in this video, which is the difference between a deterministic trend and a stochastic trend. Here are two very similar models. So model one is what we did way back in week 2. I'm going to predict y sub t as a linear function of t. The only thing that's different is I'm going to allow for my errors to come from an ARIMA process rather than assuming that they're white noise. It's important to note that this model assumes that this beta 1 is the slope for all values of t. A second model that we should consider is called the stochastic trend. So the stochastic trend is very similar to the model we had back in week 1 that we called the random walk with a drift term. The only thing that's different, again, is that we're going to have ARIMA errors instead of white noise errors. So with a random walk, our current value is just the previous value plus some drift term, so we called this the drift constant before, plus some error. So this is the model we have, but another way to think about this is if we move the y t minus 1 over to the other side, what we end up with is it's just the difference in y is equal to beta plus these differenced errors. And so our interpretation of this beta 1 is going to be as follows. If we have a 1 unit change, so if we go from time period t minus 1 to time period t, that's going to be associated with an increase of beta 1 in our y value. So we jump from y t minus 1 to, so the difference between y t minus 1 and y t is going to be beta plus some errors that are stationary. So the stationary part means that the mean is 0. Now, there may be some autocorrelations going on, but the mean is 0. And therefore, this beta 1 is telling us the change in y1 on the average. So this beta 1 is telling us the change in y on average. So it's very much like this beta 1 in the deterministic trend. What we're going to find, though, is there's additional uncertainty with the stochastic trend, and that gives rise to having wider prediction intervals. So let's go take a look at the Amazon data. So we've looked at this many times. We're going to log it, and what we see is basically a linear trend. I'd like to get rid of the seasonality, and so I'll do that using the aggregate function. We did something very similar back in week 2. Now I've got a log Amazon yearly data, and when we look at this, it looks almost like a perfect linear trend. I'm now going to try both of the models that I suggested on the previous page. Let's start out with a deterministic trend. So with the original Amazon data, it expresses time in years. If I use the sequence along command, what you're going to see is that it gives me values 1 through 17 just as a normal index. Let's go use AutoArima. I'm going to explicitly tell it not to do any differencing on this, and we're going to have it use this trend variable, so picture values 1 through 17 out here, as the x variable. We'll see what we get. So R wants to give us a couple autoregressive coefficients. Let's go write out what model has just been estimated. What we see is that there's going to be 2 autoregressive terms, no differencing, which I told it not to do any differencing, no moving averages. So here's our intercept, so 1.45 plus 0.25 times our x. So this x is 1 through 17. So what this basically says is every year Amazon has 25% growth in its sales. We also have some errors. Now the equation of these errors is this term, so let's call that 1.15 times the previous eta minus 0.47 times the eta before that, and then here is the sigma squared. And we'll just write that down. That's the variance of a white noise process. That's the deterministic approach to estimating this, this trend. Alternatively, I could fit an ARIMA 010 model. So to do that, I'll use AutoArima and just tell it to do one difference. Now what we see is that after differencing, we don't need any autoregressive terms. We don't need a moving average term. Therefore, this is my estimated model. So my estimated model is just this drift coefficient. The difference in y is just the drift plus my errors. Well, what are these errors? The errors would be the difference between two etas. The difference in my etas will be one of these epsilons, where the epsilon has the estimated variance of 0.0027. So what we see is the stochastic version gives slightly wider errors on both sides than the deterministic one, which makes the point that I just made.